Well, I was telling you regarding the free body diagram. I know that you have learned this in the last semester course mechanics, but this I am discussing one more time because we have observed over the years that the students they make trivial mistakes while drawing the free body diagram associated with the solid mechanics problem. Okay, so particularly this lecture would be helpful for those who are having little doubts or confusions. Okay, so under this topic we are going to keep 3 different problems, and it is the first one out of these 3. So here we consider a massy block that is resting on a flat plane, and that flat plane is not smooth, it is having friction. This block is having the dimension height capital H, the length 2L and the width say B. Okay, and it is subjected to a lateral force P that is acting at a height small h from the measured from the ground or the plane on which this block is resting. So we are interested in drawing the free body diagram of this block. This is pretty old problem, probably you are familiar with this kind of example, you did it in mechanics course. But the guideline is that while drawing the free body diagram you need to follow certain rules. Okay, so in the first step you need to fix a convenient axis of reference. Okay, so step number 1, you choose convenient axis of reference. Here you see x, small x denotes the horizontal axis from left to right, small y denotes represents the vertical axis from upper in the upward direction. Okay, so with respect to this axis system we are representing all the forces. Okay, so the effect of the support is accounted by these 2 forces, one is the normal force, another is the friction force F. Okay, and the weight is acting along the vertical line, okay, vertically passing through the centroid of this block. Okay, so we say that okay, this how many number of unknown forces you need to consider. Regarding that, you please follow certain rules. Rule number 1, that you first isolate the body of interest from the other parts. That means you keep the body for which you are drawing the free body diagram and delete all other parts. Okay, and then you go to the second rule, that you supply the statically equivalent forces such that the same equilibrium condition is maintained. So these statically equivalent forces, they are accounting for the effect of the deleted parts. Okay, so you see we have the 2 forces, one is the normal, another is the friction force F, but we at this moment these values are not known. When you draw the free body diagram of the support, you see we have considered the equal and opposite forces, okay, such that the Newton's law is respected. Okay, and if you just join them, you don't get any excess, you don't see any excess forces. Okay, so now in order to here up to this point, no, this free body the free body diagram, this is complete. Okay, this is the correct free body diagram. Now, if you wish to evaluate or identify these unknown forces, you need to consult the equilibrium equations. For 2-dimensional problem, you have probably there are 3 equations of equilibrium available. One is the equilibrium equation along the x-axis, another is the equilibrium equation along the y-axis, and the rotational equilibrium. Okay, so I think it would be very much useful if I talk about the reason why we have considered these 2. Okay, so what role this support is playing here? Okay, then it would be very much clear. So this support is not allowing the block to move along the horizontal direction. It is not allowing the block to move along the vertical direction. It is not allowing the block to rotate. Okay, so it is basically stopping these 3 possible or notional motions. Okay, so let us assume U to denote the notional horizontal displacement, V notional vertical displacement, and theta the rotation about the z axis. Okay, so basically it is providing the 3 constants. One is the u equals to 0, u for the entire block, v equals to 0, and theta equals to 0. So there should be 3 constraining forces, 2 forces and 1 rotational force, that is moment. So here you probably have observed that we have not kept this in the same line. Okay, we have kept it away from that, a distance away from that. It generates that moment. Okay, so let us see what are the values of n and f. So for that, what we do, we either in statement form you can write, or this is another way of representing the equations of equilibrium. That means sum of all forces that is acting along the x-axis direction. This is a sign. Okay, their sum is 0. That implies that P minus F equals to 0. Okay, so then second equation of equilibrium equals to 0. That means sum of all forces acting along the y-axis direction, their sum is 0. That means N should balance W. Okay, and then the rotational equilibrium. This is something little bit different. Okay, so what I am writing, this sum of all moments coming from the forces generated by the applied forces, including the externally applied moments, if they are present, their sum about a point O should be 0. Okay, so that implies that we have here A times N minus H times F P should be 0. Okay, one thing I probably have I forgot to mention, that this time we are choosing this point as the O. Okay, so we are taking the moment as the moment coming from all the forces, okay, about this point. So naturally, since we have selected this point and we see that okay, W and F, they are passing through this point, they have 0 contribution. The only contribution that the effects will come only from N and P. So A times N, that is the amount of moment coming from generated by N, and H times P, they must balance each other. So you see, you get this distance. Okay, so it is not 0. It has the dimension of length, since the load ratio, which is the dimensionless quantity, is involved, and it is having the length dimension. Okay, so I think up to this part it will be clear. Okay, one thing you need to know, that A cannot take arbitrarily large value, even if you have very large P. Okay, so there are special the unusual cases. Okay, so we say that okay, A must be, in order to have a meaningful answer or the explanation, you need to have this situation. The equality case is different, otherwise A must be less or equal to L. Okay, less than L. Okay, so now let us see whether this N conveys the actual message or not, actual representation of the contact. Okay, what this contact is offering, whether the N says everything about that or not, N and F. Okay, so probably you know that it is a distributed, you do not have the single point of contact. Okay, you have a zone that contains infinite number of points. Okay, so you basically get a distributed force. Okay, distributed intensity. In the case where you do not have any P, this is uniform. So you get uniform normal reaction. I am talking about only N. Okay, on normal reaction. Now, how much is the value? Weight divided by the contact area. That means the W over the 2L times B. Okay, that is the intensity. And when you have P present, then this situation becomes different. Okay, so you get the distributed force, which looks like this one. Say trapezoidal distribution. You see the resultant of this distributed normal reaction is N. So it gets shifted. Okay, so this resultant it passes through the is vertically, okay, passes through the centroid, okay, but here it is getting shifted. Okay, so that's why you have to understand. Okay, this is the normal reaction. Okay, coming with whose resultant is n. And now I told you that A should be less than L, and when A hits the value L, then you get a special, a different, completely different situation. Okay, so and I believe that requires a discussion. Okay, you have this situation. Okay, so you see when the resultant from this trapezoidal distribution, you can just work out the geometry. Even if you consider this value 0, you get a triangular. Then also you see that small a cannot be L, small l. Okay, it is always less than small l. Okay, when you consider a equals to L, that means you basically assume that there is only one point of contact, single point of contact, that is the vertex. Okay, so the whole n is acting at that point, f is also passing through that point. That means this body is on the verge of toppling. Okay, so beyond that point we are not allowed to go, because this discussion won't be valid at all. Okay, so I think I have made it clear. So let us stop here and let us go to the next problem. Okay, it seems that I have missed a small point. This F is the friction force that takes the value of P, we have seen. But according to Coulomb's law, F has certain limit. Okay, so that limit, F max, we can say that which is proportional to the normal reaction, and mu plays the role of proportionality constant. This mu takes different values, okay, and that depends whether you are considering the static situation or you are considering the dynamic situation. Okay, in both the cases you get the same this structure. Okay, F should be less or equal to m. Okay, that is the important thing to know. Other things I think you know all. Let us go to the next topic. Coming to the second group of problems, here we consider two different beams. The first one, it is subjected to the uniformly distributed load of intensity Q up to certain lengths. Further, there is a concentrated force P at some location. Second one, the entire span is subjected to the uniformly distributed load of intensity Q. So there may be a situation where this distributed load may not be uniform. Okay, so we are not considering that at this moment. The first case, the beam is simply supported, we say, that means one end is pinned or hinged, another end is roller, having the roller support. Second one, we have the left end clamped, the right end it is propped, there is a roller support or rocker support here. So they represent the same, they convey the same message about the kinematic constants. Probably this situation you all know. So where these members are considered as the two force members, and there is a pin support here, there is a roller support here. So you consider till so far what you have done, you have considered the entire part as a single entity, single structure that is supported on 2 points A and B. So where A is a hinge and B is a roller. Now we come to these individual supports and we shall analyze. While drawing the free body diagram, what would be the constant forces required? So before going into that, so what we need? We need to set up a reference axis. This is step 1. Choose a suitable reference axis. Here for convenience, what we are doing, we are using the letter X to denote the horizontal axis, letter Y to denote the vertical axis, and the Z axis. So about that there is a rotation, possible rotation. So theta denotes the rotation about Z axis, U denote the possible displacement along X axis, V is denoting the vertical displacement or the displacement along the Y axis. You consider this case where this joint is hinge joint. This is a member, extended member, so we are not extended it. This is a formal representation, that means that this part is extended. So we see the meaning of that, the representation. This kind of representation means the displacement is not allowed in the x direction, displacement is not allowed in the along the y direction, but this member is free to rotate about z axis, about this point. Okay, so we have actually two kinematic constants, u equals to 0, v equals to 0. So when you draw the free body diagram, you identify two constant forces. The Fu is the constant forces for the constant u equals to 0. Fv is the constant force that corresponds to the v equals to 0. When you come to the second type of support, that means the roller support, here you see this part, this joint or this support, it is free to move along x-axis direction. However, it is not allowed to move along the y-axis direction. Again, this part of the beam, it is free to rotate about z-axis, about this point. Okay, z-axis passing through this point. So actually here you get only one kinematic constant, that is v equals to 0. So when you draw the free body diagram, you see there is a beam. So let me correct this diagram or making it consistent with the previous diagram. Okay, so what you need to apply only one constant force that corresponds to v equals to 0. When you have the clamp support, you see this clamp means the displacements as well as the rotation is not allowed. That means u equals to 0, v equals to 0 and theta equals to 0. So you actually have three kinematic constants. So when you draw the free body diagram, actually you need three different kinematic constant forces. The Fu corresponds to u equals to 0, v that corresponds to v equals to 0, and m, the constant moment, the constant force, rotational force, m corresponds to theta equals to 0. So when you draw the free body diagram for the external part, that means when you remove this support, then you get this representation. So this is the beam we are drawing. So we write the external load, distributed load, and there is a concentrated load P. So this is Q per unit length, and you see if we remove this one, so we are going to supply the statically equivalent constant forces. So that is this force. Okay, we have used the letter A to represent that, to identify that end. So one choice may be AY and AX. Okay, and here you see you get this force. So this is the free body diagram for the first example. Second one, you take this one. So you basically get the loading effect, all the forces, it is uniform, that's why intensity Q per unit length, and this end is clamped, so there would be three constant forces, A, Y, A, X and M, A, and here you get B, Y. So, whether the number of unknowns are more than the number of equations, that we shall discuss later. Okay? So, at this moment we see that okay, when we draw the free body diagram, that means we actually do not know about these quantities. How much is Ax, how much is Ay, how much is MA, and how much is By, that we need to solve. Okay? So, in 2D, two-dimensional problems, actually you have three number of equations of equilibrium, three equations of equilibrium that are available. One, the translational equilibrium equation along x-axis, translational equilibrium along y-axis, and the rotational equilibrium about the z-axis. Okay? So, with this I stop for now. Okay? This second part is over. Now we shall discuss the third situation, another case of problems. So, coming to the last part of this session, we have taken the same problem what we have discussed in our last session, a previous example, okay, under 2 by 3. Okay, so here you see that okay, we have removed all the supports and we have supplied the statically equivalent forces that maintain such that the equilibrium of the entire structure is maintained. So, now our notion is a little bit different. What we are going to do, we are going to just consider the free body diagram of a part of this beam. So, let us consider a section and let us try to draw the free body diagram of the right part with respect to the assumed cut section. Okay? So, you remember the rule number 1, that the portion of interest you need to draw it, okay, and delete all other parts. So, let us see, if we take this one, we see that okay, here B y is acting, P is probably acting here, and here this is the cut face. Okay, here we need to provide the statically equivalent forces such that equilibrium of this portion is maintained. That means same equilibrium condition. What was our equilibrium condition? This boom, entire structure is not moving in this x direction, entire structure is not moving in the y direction, and it is not rotating. So, notional displacements are u, v, and w. Okay, u, v, and theta. Theta is the rotation about the z axis. So, if you talk about the left part, we see that okay, we have a y, we have a x, and then we have the loading q per unit length. Okay? So, what would be the consistent constraining forces? In order to understand that, you need to identify what are the kinematic constants we have at this section. Okay, so in order to illustrate that, we need to consider a big picture, and here we assume that this beam is prismatic and having a rectangular section. You see here, that means the section shape and the size, that is not changing, okay, as we move along the length of the beam. So, this is the right part, say, left part, say, and consider the right part. You see, the left part and the right part, there is a gap. This should not be there. Okay? There should not be any gap or overlap. You can consider this situation also. Okay, so gap or overlap is not allowed. Okay, so gap and overlap is not consistent with this one. So that is a kinematic constant. So you see gap or lap should be 0. That is the kinematic constants. And who is going to take care of that? We assume that the normal, the axial direction, some force in. So let us draw this one. In. Okay. So once this kinematic constant is identified, you identify the conjugate constant forces. Now let us come to the next kinematic constant, that relative slide between the sections that is not allowed. Okay, let me illustrate this one. We are splitting this beam into this structure into two parts for our own convenience, but actually they are integrated. Okay, so when you study, that should be considered. Okay. So you need a constant force such that this relative slide becomes 0. Okay. So either in this direction or the opposite direction. Okay. And for that, what you need? We say that we need a force V. So we are going to consider this one, V. Okay. And then we come to the last another kinematic constant. So if you arrive from left, you identify this cut face with a particular orientation. When you are coming from the right, you should get the same orientation. Okay. So there should not be any kink. Okay. So with these two constants, you see that this point, these sections, there is no relative gap, this gap or overlap, and there is no relative slide. Okay. But still there is one possibility, that is the kink is possible. Okay. Formation of kink, it is not suppose this is the left part, you see this point, so you take this one, suppose this is the beam, this is a section, here this point you get they are having the contact. Okay. So there is no gap or overlap or slide at this point, but when you go away from this point, consider this one at this level, you see the gap. This should not be there. Okay. So relative change in slope. Okay. Okay, so that or the slope jump should not be allowed. That is a constant, kinematic constant. So and what is the constraining force? Here we say that it is M. Okay, so okay, with this I think the free body diagram or where the internal force of resistance is shown. So with this the free body diagram is complete. So this is the free body diagram for the right part, whereas the other part is the free body diagram for the left part. Okay. So what we have learned, we have seen that jump in u should be 0, the kinematic constant. Jump in v should be 0, second kinematic constant. Theta should be 0, that is also the kinematic constant. So 3 kinematic constants are identified, 3 constraining forces we have supplied. Okay. So you have to remember the rule. First of all, the portion which you are considering, you keep that, and other portions you delete. Okay. So the contacts, at the contact faces, you supply the statically equivalent forces. For that, you need a proper understanding to identify the kinematic constants, and you supply the conjugate forces. So I think I can stop with this, and we shall move to the next topic.